welcome everyone. Good to see all of you for the last class, right? So no more, we have our final next Thursday, but this will be our last in-class meeting. We're going to take a look at, what are we doing? 14.5. I'll send out an announcement, but I'm looking over my schedule. I'll have some open office hours for review for just this class. I'll do it Tuesday at 3 till, what's I going to do it? I think 3 till 5. What I will do is I'll send out an announcement, and once it's open, we'll answer any of your questions. But if there's nobody there, I'm not going to stay on for a long time, so let me know if you need to meet. You can also contact me for individual Zoom meetings as we have time. But the best preparation for the final is right down in here. And basically, if you'll go back and review exam 1, exam 2, exam 3. The final exam is, I looked at spring's version. I don't have this version, but it was, I believe, about 17 questions. So a little bit longer than what we've been doing. Been about 12, so a few extra questions. But there will be one type of question from each of the exams. There'll be one exam question from each of these last 3 units that we haven't tested you on yet. But as you see, what we're doing is these last 3 units are really nothing new as far as technique. They're more about an application, okay? So one from each of these sections, and then sort of goes over each of the exams. And they, at least in the spring, the questions on the final exam were very similar to the types of questions that were on the midterm exams. Some of them even formatted the same way with just different functions and such. So know how to find a critical point, know how to find minimums and maximums, all those things that we've tested. But that's what you'll need to do, is kind of go back and review over the 3 exams. There's study guides, there's video solutions, but there's not really just one sort of comprehensive new review for the final. Yes? There won't be a separate one, no. So just the final, there'll be basically 3 questions. So you get a question on each 13 or 14.3, 14.4, and 14. There'll be one question on each of those. 12.6 is still extra credit, and it won't be on the exam. Yes? There is no separate formulas. However, for like the consumer surplus or producer surplus, they do provide that one. If they're going to do the volume of a sphere, they provide that. So it's just like on the other tests. There's no separate formula sheets. So you need to know how to take a derivative of a product, derivative of a quotient, a chain rule. You need to know how to apply those, but there's no formula sheets on those. But what you might want to do is make your own formula sheet, study it real well, and maybe right up until the point that I pass out the exams, look them over, and as soon as you tuck it underneath and get your exam, start doing a memory dump and make your own formula sheet. So if you have any that, that you're starting, so that there is a way you can carry the formulas in here. And oftentimes when you start working an exam, what you thought you remembered gets scrambled a bit. So if you can organize things on a short card and then just kind of spend some time memorizing it, tuck it in with your stuff as soon as the tests come out and write that down. That will help as you go through there, because you're going to get, again, it is comprehensive. It's a whole semester's worth of work. But that's kind of the best way that I found that will work. Make sense? Okay. So let's go ahead with our last concept, and this one actually ties us all the way back to where we started with limits. So let's go ahead and get into here. So improper integrals and applications. So bottom line is we've been, oh shoot. This was working earlier. Okay, good. It's been one of those days where nothing seems to keep working right. Okay, so we've been taking this sort of integral, going from some number A to some number B. So those are finite or definite numbers, a beginning and an end. What we're going to look at is what happens if one of these endpoints is not really an endpoint, but infinity. So it kind of goes on for a long time. That's what we would call an improper integral. Okay, because basically it doesn't end, right? So what does that look like? We're either going from some starting point to positive infinity, or we're coming from negative infinity up to some endpoint, or potentially infinity in both directions. What this infinity means is that the variable gets very large. Oftentimes in business, what your variable is time. So the application for business when we're doing this to analysis is we don't know when the end comes. We don't, it's just off in the future. It's some distant time, and we're sort of trying to do long-term planning, but we don't know if it's a year, 5 years, 10 years. We call that infinity. So it's not really forever, but it's when we don't know what that endpoint is, we can do this kind of analysis. There's two things that can happen. I think that's on the next page. It can either converge, so the function, even though it's going to infinity, will actually be a set amount. Basically, even though you're getting out to infinity, that you're adding such a small amount, it doesn't matter. Okay, so converges, it gets to a figure, or it goes off to infinity, and we can't calculate, we can't get a number, we'll say that diverges. So one of those two things. If it diverges, it's not very helpful for us. It doesn't help us plan off to the future. It means basically, you got to give me an endpoint, otherwise I can't give you a value. If it converges, then we can say, if we go long enough, this is what it's going to end up being. Okay, and we'll look at that. And what we're going to do is, there's one of the next slides, I think it might even be the next one, I bring back from 10.3 the stuff on limits. Yeah, good. I even remembered. So one of the big ones we get, so a couple things can happen with these. If we get division by 0, remember, we think of that as going to infinity, either plus or minus. That's diverging, right? There's no set number. So if we do these integrations and we get something going to some kind of division by 0, we'd say that diverges. All of these right here that are going to infinity, and k is just some kind of constant. So if you've got an infinity dividing by some constant, all of these go to infinity. All of these are said to diverge for the purposes of what we're doing now. Okay, there is one that we'll look at, and that's if we divide by infinity, and we're going to see, taking the limit of that, that goes to 0. That's converging, right? That's a value. And sometimes a part of it converges and some of, we'll see how that applies. So this is the one we want to remember. Division by 0 will converge, division by infinity goes to 0. The other important one is this one here. That's when the exponent goes to negative infinity, because remember, that's a reciprocal. That's really what's happening is you're dividing by infinity. So that also goes to 0. So those are the two ones we want to remember. Those are what's going to converge. Everything else will diverge. So this one, to a positive exponent, it diverges. Okay. So and basically what we'll do is we'll treat this, when it says it's going to infinity, we'll give it a label. They usually use m, some number. We go ahead and integrate. We plug in like we've been doing using the FTC, the fundamental theorem of calculus, and then we use limits. And again, what we're going to be looking for is just these two things here, either division by infinity or an exponent that's raised to a negative power going to infinity. So those will be the two things. Okay. So this is sort of the little trick. Instead of using infinity, we say, oh, let's just call it some value. We could have called it little a, but whatever that is, we'll say, we'll just treat this as if we're doing everything. And then once we integrate it, we get the integrated value, right? And we were calling it like big F. We would go from M to B. And so we get big F at B minus big F at M. And okay, this is going to be a number. And then this one we're going to have to use limits on. And the same thing down here. In the homework, I didn't see any that had infinity at both ends. I saw one that had, most of them have infinity at the top end, and one or two will have infinity at the bottom end. So we're only going to have to do limits on one of the sides rather than both of the sides. Okay. So this is kind of, I didn't set this one up quite like I wanted, but let's do this. So let's talk through this. So we're given this as our example. We can think of this as the integral of x to the minus 2 dx, right? And just kind of just think in general. When we integrate it, what do we get? We add 1 to the exponent and divide by that new exponent. So we're going to get x, negative 2 plus 1 is negative 1. And we're going to divide by this new exponent, negative 1. So that gives us negative 1 over x. And again, we're going to go from 1 all the way to m. If you want to kind of shortchange this, you could always, what I kind of like to do is, instead of using this extra little step here, I just go ahead and put infinity. Because watch how this works out. So when we analyze this, we plug in infinity for x. So that's minus 1 over infinity minus negative 1 over x. And we plug in 1 for x. So you see how that worked? So we just integrated 1 over x squared, as we've been doing. So that's negative 1 over x. We plug in the two limits and just think of it as going from 1 to infinity. And we don't have to use all this notation. And then remember, what is 1 over infinity when we looked at that sheet? If we divide by infinity, what do we get? 0. So that's why it's right there. That's one of my things I'm looking for. Instead of writing, 1 over m and m going to infinity, hey, this is just 0. Negative 0 if you want. I got negative, negative 1, so that's negative and negative make a plus 1. What's 0 plus 1? 1. Okay. I think that's why I left it here, because they use all this notation. I said, let's just cut to the chase. Let's keep it 1 to infinity. And then let's just plug in infinity for x. And because there was only two things, right, that converged. 1 over infinity goes to 0, and an exponent with going to negative infinity also goes to 0. Those are the only two things that converge. Everything else diverges. So we're good there. Does that make sense? Okay. And most of these, what they'll ask you these two questions. Does it converge? It's either yes or no. So, and you don't find out until the end. And what does it converge to? So it's kind of like at this point we found, oh, it went to 1. That means it converges. We're going to see some that don't go to a number, it goes off to infinity. That diverges, and then we don't have to do anything more than say that it diverges. Okay. So here's an example. Let's see if we can set this up. By 2009, music downloads were making serious inroads into the sales of physical CDs. Approximately 290 million CD albums were sold in 2009, and sales declined by about 23% per year the following year. Suppose this rate of decrease were to continue indefinitely. Okay, so that's where the infinity comes in. We don't know when this will stop, but let's see, it goes on forever and continuously. So someone was asking this question about continuous interest. So notice that's a 23% decrease continuously. So not periodic decrease. So what does it mean if it's continuously decreasing? We have a formula. If we think of interest, PE to the RT, that's continuous interest. Do you remember that one? Hopefully, because that's not, again, we don't have a formula sheet. If you don't, write that down somewhere, right? So the accumulated value is this. How many CD albums total would be sold in 2009 on? Okay, so from 2009 on. So what we're asking is the rate of decrease, remember, is what we're starting with. Our rate is going to be 23% decrease is going to be negative 0.23. So this becomes E to the negative 0.23 T each year. Okay, so that's our formula. What we want to see is what would be the accumulation of sales over a long period of time. So what they're asking us is we're going from 2009, which was sort of the starting, so we can call that year 0. And we're going to go indefinitely. We'll call that infinity because, again, an unknown ending point. Not really forever, but you just want to see what happens. And then we've got our formula, 290 e to the minus 2 or 0.23 t dt. Is that making sense so far? Following along? Any questions? Okay. So again, I'm just going to go along with this infinity part. When we integrate this, what do we get? 290 e to the minus 2 or 0.23 t all over negative 0.23, right? Because we have to, when we integrate, if we were to take the derivative, it's its own, remember E is its own derivative, it's its own integral, but if we were to take this derivative, this would come down, and since it's not there, we have to do this. So this is the little shortcut rule. And you'll be doing, on the exam, you'll be doing this type of integration multiple times. I think the shortcut rule shows it as e to the at dt. Whenever you integrate that, you're going to get e to the at divided by a. And a is just a number, whatever that number is. Okay, so remember that one as well. I guarantee you, you will use it at least once on the exam, maybe twice. Okay. Okay, we okay? And then we're going to take this one from 0 to infinity. Okay. So what does that give us? That gives us, we're going to plug in infinity on the front end. So that's 290 e to the minus 0.23, sorry. What was this? This was dt. Minus 0.23 times infinity over negative 0.23 minus 290 e to the minus 0.23 times 0 over negative 0.23. Okay, that's the fundamental theorem of calculus, FTC. Sometimes they'll mention that. Again, I don't really care what things are called, but if you see it on, you just got to be able to know on the exam when they say use the fundamental theorem of calculus, this is what they're talking about. Plug those in. That's all it is. Okay, you okay so far? All right. So using our ideas of limits, what is this going to be? The main part we have, it's e to some negative power, 0.23 times infinity, still infinity, right? E to a negative infinity. Do you remember what that went to in our limit chart? 0, right? Because e to a negative power is like 1 over e to a positive infinity. So it's like the denominator is going to 0, or going to infinity. This part goes to 0. Okay, so this whole front part is going to be equal to 0. And then we've got a minus down here. What is e? Negative 0.23 times 0 is 0, right? What is e to the 0 power? 1. Everything to the 0 power is 1, pretty much. So that's 1. We end up with just 290 divided by 0.23, right? That's going to give us a value. Did I bring my calculator? I didn't bring my calculator. But that's what phones are for, right? They've always got a calculator with us. So we'll take 290 divided by 0.23, and we get negative and negative, so that's going to give us a plus. I get 1,260.87. If you round it, it depends on how many decimal places they want. And that's in millions, right? So let's write this down. 1,260. You could round it maybe, I don't know. They didn't say what to round it up. I think if I left everything, this is all going to be worked out for us to check anyway. Hopefully I got the right answer. I didn't look over this stuff in advance, but does that make sense? Okay, so we just come here, say, okay, this one, this whole thing goes to 0. If this goes to 0, 0, 0, so it's all 0. This just goes to 0. This part here, this becomes 1, so it's 290 over that number. Okay, and let's see what we end up with. Oh, shoot. Oh. They did it slightly differently. They're I read this word continuously as continuously decreasing. That's why I would use the continuous interest, continuous decreasing. They are actually doing a periodic. So I disagree with what they're doing unless they didn't really mean that it's continuous. What they're doing is an annual rate of decrease, right? So if we use continuous interest, which I would hold by, is negative 0.23 in this formula. Otherwise, you take 100 minus 0.23 and you'll get negative, or you get 0.77, right? 100 minus 23 gives you 0.77. Again, that's a periodic, that's an annual, that's what that's saying. But I think we'll come up pretty close. Yeah, they got, because then you've got to have the log when you do it. Pretty close, 1,100. We had 1,200 because we had truly continuous. It's continuous. Theirs is only annual. But notice our numbers are about close enough. Just they didn't use the continuous, which I don't know why they didn't. On our exams, we use the continuous. So if you'll notice on all the exams, we only have you integrating E. We don't have you integrating like 0.77 as a base. Questions? Does it confuse you that they did something different than I did? Confuses me. I don't know why they would say continuous and then not use continuous. That's the only reason you use continuous. When you say continuous to a mathematician, they'll go to E. All right, we good with that one? Sort of? Okay. Now these ones, it'll have definite endpoints, but what we end up integrating, sometimes we might have a problem, okay? So something like this. So notice the limits are not going to infinity, but if we integrate this and we still have something in the denominator and we try to plug in 0, what's going to happen? What is 1 over 0? Undefined or infinity from our limit chart. We could call it infinity, and if it goes to infinity, it diverges, right? And that's kind of why if one part of an equation is undefined or going to infinity, the whole thing is kind of undefined. So what we would do, right, this is from 0 to 1, x to the negative 0.5 dx. Let's see. This one might, let's see. This actually still might exist when we go through it, but if you were to try, if you did the graph, and I think they show it next, let's see. Yeah, they show if you were to graph it, that as we go to 0, this, you know, the function itself is going off to infinity. But watch when we integrate, which they'll do on the next page. So x to the negative 1/2, right, because a square root is a 0.5, it's a half power. It's in the denominator, so we bring it up, it's negative. How do we integrate? We add 1. So negative 0.5 plus 1 means we're going to get x to the positive 0.5 power. And we're going to divide by that new exponent, 0.5, and we're going to go from 0 to 1. This is defined. Okay, this is defined. So we couldn't plug in 0 here, but we can do it here. So we plug in 1. So you get square root of 1 over 0.5 minus the square root of 0 over 0.5. Square root of 1 is 1. Divided by 0.5 is 2. 0, square root of 0 is still 0. 0 over 0.5 is 0.5, so this should be 2. Should be an area of 2. And you can kind of see that this is an area of 1. All this area would add up, should add up to another 1. Okay, but again, what they're saying is they go through a lot of effort to say, okay, let's just see if we can sort of take the limit on this side. And again, they do a lot of sort of work, but for me, you know, for if you're a math majors, this is kind of what they want you to see. But see, we didn't have to go through all these little steps. We can say, let's just integrate it first and see if we can plug in 0 and 1. Let's not worry about it. If you try to do this graphically at the beginning, it might not look real nice. Again, they were doing the graph, but notice we can plug these in. And in the end, we just end up putting in 0 here. So R goes to 0. Okay, that's just 0. There it is. Okay. So on these, go ahead and just integrate it and then plug them in. I think the next one, we've got one example where we do run into a problem, and what we'll say, okay, that one diverges. which the integral becomes infinite. Okay. Let's see, where are we getting towards? Basically, I think that was left over. So we've already addressed this, that if B, yeah, so again, if A and B, if you've got set intervals, just go ahead and integrate it. And if you're able to plug in those values, it will converge and it's got a value. If when you go to plug them in, and I think there's one in the homework because you're integrating 1 over -3, so your end result is 1 over -2. And when you plug in 0 there, you're getting 0 in the denominator, and that's undefined, right? That diverges. So there's a possibility when we've had these that we haven't talked about, but just go ahead and work them without all this sort of extra notation. Just integrate them, plug in the values, and if it diverges, then we just say it all diverges. It doesn't have a value. Okay. So there will be a few of those, yes. Actually, D and E, it'll tell you. So in the homework, that there's the first question that says, does it converge or diverge? You just click the button. And I think if you go to, yeah, if you say diverges, below it says if it diverges, do D and E. So look at the yeah, I think that's where the instructions. So you either put in a number or D and E for the value, and then it knows. And I did a few of them, and yeah, I think there was one. It's one. You're integrating 1 over x to the third. So when you integrate that, you get 1 over x squared. When you plug in 0, that diverges. It goes to infinity, right? So when you go through this one, sort of the main part you want to come back is it's really doing everything we've already done, but just look, take a copy of this page. There's only 2 times it's going to converge. That's if I've got something to a negative exponent, e, and most of the time it's going to be e, or if I end up dividing by infinity, that'll go to 0. Everything else diverges. So just treat everything. Don't worry about all this limit notation stuff. Just treat it like we're doing. If it's going to infinity, plug that in, and there's 2 places just like they have here, and those things will converge. Everything else diverges, and you'll be safe. And if they have a problem where they say continuous and they don't use continuous, let me know. But I don't think there was one in the homework like that. Okay. So where do we use this? Again, just in making business plans when there's an indeterminate end. Okay. Goes to infinity. All right. That's all I got for you. What should you be doing over the weekend? Partying and having fun? No. That's the last weekend. That's next weekend. That's the weekend after this, right? Enjoy, but study for the final. If you've been doing well on the 3 exams, what you'll see is you're pretty much ready to go, but go back over it. But go back over those 3 exams. Go back over what you struggled. Also remember to go back over what you did well at. So that's also fresh. And I think it's a great idea, make a note card of your formulas, of sort of, maybe a note page, and just so that you get it all together in your mind of all the things we've done. Bring it with you to the test. Look at it right up until the last minute, and then copy as much of it that you remember onto a piece of scratch paper.